Yes. Hello friends, welcome to the session, continuation of chapter 5, power measurement. Now in this session, we will start with power measurement using wattmeters. That is, wattmeter in the sense mainly concentrate on EDM wattmeter, electrodynamometer wattmeter. I am discussing EDM wattmeter. Yes. The first you concentrate some theory points with respect to wattmeter. Later we will see how to measure the AC power by using wattmeters. I told already how to convert electrodynamometer as a wattmeter. In the discussion of EDM instruments, I given one statement. We know that electrodynamometer instrument minimum consists of 2 coils. If it is a 2 coils, how to convert as a wattmeter means current coil is connected in one line, pressure coil is connected current coil is connected in series with load, and pressure coil is connected across the supply, then it acts as a wattmeter. That is, this is the fixed coil. It consists of 2 coils. One is fixed coil, another one is moving coil. Fixed coil is connected in series with load. Fixed coil is connected in series with load. In series with load. Yes. And moving coil is connected across the supply. Moving coil is connected across the supply. Okay, this is LP and this is RP. This supply we are giving. Okay, let this current is I, this voltage is V. Now this coil is fixed coil and this coil is moving coil. Okay, now first we concentrate on the construction details with respect to fixed coil and moving coil. One is fixed coil. Yes. Fixed coil is connected in series with load to carry the high currents. One is it is connected in series with load. In series with load. Yes, to carry the high currents. Carry the high currents. Yes. One more point to remember. Actually, this terminal is main terminal. This terminal is common terminal. This is voltage terminal. This is line or load terminal. Because it is at supply side, that's why main supply side, main terminal. This is load side, load terminal or line terminal. By using this terminal, we can decide the voltage rating. And this is common terminal because this is common for MC short and LC short. There is a 2 types of wattmeter connections. One is MC short connection, another one is LC. This is also wattmeter connection. This is also this is LC short wattmeter. And if you connect like this, then it is MC short wattmeter. Where you can use MC short, where you can use LC short, later on I will explain. Okay, that's why this is common for LC short and MC short. That's why it is called common terminal. Okay. Now it is connected in series with load to carry the high currents. Then if you want to carry the high currents means it must have the less resistance. That's why it is made with less number of turns, having low resistance, and it is made with a thick wire, and it is a thick wire. It is similar to that of series field winding in the case of DC emissions. That's why it is made with less number of turns, having low resistance, and it is a thick wire. Why I am telling that it is a thick wire means we know that R equal to rho L by A. At a given length, if you want to maintain the low resistance, the cross-sectional area must be high. If the cross-sectional area is high means it is a thick wire. Then its excitation is proportional to load. The excitation of the fixed coil is proportional to load. One more point to remember, fixed coil is also called, different names, is also called field coil, parallelinodum, field coil, or current coil, or yes, simply CC of wattmeter, current coil of wattmeter. Now it is called CC of wattmeter. We know that in the representation of this current coil, it is represented with 1 or 2 turns only because it is made with a less number of turns. The excitation of this coil is proportional to the load. If the load is increases, the load current is increases, the current to the current coil is also increases. Okay, these points you remember with respect to fixed coil. The next one is moving coil. Tell. Yes, it is connected across the supply. Moving in general, it is connected across the supply. Then it is made with more number of turns, having low resistance, more number of turns having high resistance. If the resistance is high means cross section area is less, that's why it is a thin wire. It is made with more number of turns, having high resistance, and it is a thin wire. One more point to remember, its excitation is proportional to supply voltage. Its excitation is proportional to supply. Yes. Then this moving coil is also called S voltage coil, or potential coil, or pressure coil, or simply PC of wattmeter, pressure coil of wattmeter. Now, this moving coil is also called pressure coil. Okay, these are the points you remember with respect to fixed coil and moving coil. But you have one doubt here, sir. Fixed coil is also having resistance and moving coil is also having resistance. But no doubt at all, it is a low resistance, it is high resistance. But in the representation of fixed coil, we are not representing in series with resistance. But in the representation of moving coil, we are represented in series with resistance. No doubt at all. We can also represent like this. This is also wattmeter. But what is the significance of representing a pressure coil in series with resistance? What is the significance of representing a pressure coil in series with resistance? Means this indicates that this coil is having high resistance, and not only coil resistance, some extra resistance is also connected in series with pressure coil. That is the significance of representing a pressure coil in series with resistance. Not only coil resistance, some extra resistance also connected in series with pressure coil to maintain the high resistance. What is the need of maintaining the high resistance for pressure coil? To measure the true power. This very important statement. This write as a note already framed in compute exam. To measure the true power. To measure the true power. Yes. To measure the true power, pressure coil must be highly resistive. Pressure coil must be highly resistive. Highly resistive. Okay, pressure coil, but purely resistive not possible. That's why you take the highly resistive. In the options, to measure the true power, pressure coil must be highly resistive, purely resistive, highly inductive, purely inductive. Purely resistive is also there, but purely resistive not possible. That's why your answer is highly resistive. To measure the true power, pressure coil must be highly resistive. That's the reason why we are representing like this. Okay, this is some introduction to the wattmeters. Now, with this knowledge, how this wattmeter measures the single phase AC power, that I want to discuss. That concept I want to discuss in two cases. One is true power, another one is measured power. True power means that is ideal case. Practically, the wattmeter cannot measure the true power, it measures the measured power. First, I am discussing the case one is true power concept, then measured power concept, then measured power is not equal to true power, there is error. Then I want to calculate what is the error, then what is the reason for error, then how to reduce that error. Okay, first put the siding, single phase power measurement using EDM wattmeter. Yes. Concentrate single phase power measurement using EDM wattmeter. Yes. How to measure the single phase power? How this single phase EDM wattmeter measure the single phase power? That you concentrate. You know this current coil is connected in series with load. In series with load. Moving coil is connected across the supply. LP is pressure coil inductance, RP is pressure coil resistance. Let the supply voltage Vs equal to Vm sin omega t. Yes, and this current is I, and this voltage is V. This current is instantaneous value of pressure coil current IP. This is a current coil current ICC. This is phase, this is neutral. Okay, where LP is pressure coil inductance, pressure coil inductance. RP is pressure coil resistance, pressure coil resistance. Okay, now first I am discussing with case 1. In 2 cases I want to discuss this concept. Case 1, let pressure coil inductance is negligible. Pressure coil inductance is negligible. Pressure coil inductance is negligible and pressure coil is highly resistive. Pressure coil is highly resistive. In case 1, I am assuming that pressure coil inductance is negligible and pressure coil is highly resistive. Okay, now tell me, we are giving the supply voltage is Vm sin omega t. Let capital V equal to Vm by root 2. This equal to RMS value of supply. RMS value of supply. Okay. Now we are giving V equal to Vm sin omega t. Because of this Vm sin omega t supply, there is a current through pressure coil. Now I am writing the instantaneous value of pressure coil current. The instantaneous value of pressure coil current equal to Vm sin omega t by, shall you take RP or ZP? You take RP, because I taken pressure coil inductance is negligible. PC inductance is negligible and pressure coil is highly resistive. That's why IP equal to Vm sin omega t by RP. Shall you write like this? This Vm I written in terms of RMS value of supply root 2V. That is root 2V sin omega t by RP. You also write like this, the instantaneous pressure coil current IP equal to root 2 capital IP sin omega t. Root 2 capital IP sin omega t. What is the capital IP here? RMS value of pressure coil current capital V by RP. RMS value of pressure coil current. Okay. Now that means if this voltage is given, this is the current passing through the pressure coil. Similarly, I want to find what is the current passing through the current coil. Then for that, let us consider the vector diagram. Let the reference is supply voltage V. Assuming that lagging power factor loads. These are, I am discussing this concept is lagging power factor loads. Assume that loads are lagging. Case 1 is lagging power factor loads. Throughout this concept I am explaining for lagging power factor loads. This case 1 I am explaining for lagging power factor loads. Okay, if it is a leading, how to write the formulas directly later on I will give, but throughout analysis assume that lagging power factor loads. Okay, now let the supply voltage is V. This is the voltage, the supply voltage V. RMS value of supply voltage is V. Now, what about the pressure coil current? The pressure coil current is lags the voltage or leads the voltage or in phase with the voltage. Yes, in phase with the voltage, because we are assuming that the pressure coil inductance is negligible, it is having only resistance. That's why pressure coil current is in phase with the voltage. But what about the load current? Because we are assuming that lagging loads na, load current lags the voltage. Load current lags the voltage by angle of pi. We are assuming that lagging loads, that's why load current lags the voltage by angle of pi. Now, I equal to ICC. This ICC and I is same, but I lags the voltage by angle of pi means ICC also lags the voltage by angle of pi because of lagging current. Now you tell me, what is the expression for ICC? The current coil current equal to root 2I. Generally, how to write instantaneous value of current? ICC equal to Im into sin omega t. But that Im I am writing in terms of RMS value. That's why RMS current is I. Root 2 you multiply, then you can get maximum value. Root 2I is maximum value. Okay. Root 2I sin omega t minus pi. Why I taken minus pi? Because this current lags the voltage by angle of pi. That means, if the voltage is applied to the wattmeter, now there exists two currents. One current is, that is the current through the pressure coil. Another current is current through the current coil. Now tell me, what type of wattmeter this one? Yes, electrodynamometer wattmeter. Means electrodynamometer instrument we are using as a wattmeter. But internally the concept is EDM instrument concept only. But here we are converting as a wattmeter. Now, we know that in EDM instrument, two different currents are passing through fixed coil and moving coil. That is current coil and pressure coil. There is instantaneous torque is produced. Then what is that instantaneous torque? The instantaneous torque produced because of these two currents. Because of these two currents in the wattmeter, there is instantaneous torque is produced. What is the expression for that instantaneous torque? IP into ICC into dm by d theta. The same formula is given in EDM instrument. I1 into I2 into dm by d theta. Instead of I1, I2, you are substituting IP and ICC. Why I am using this equation? Because it is a which wattmeter? EDM wattmeter. That concept we are utilizing here. Understood? That is IP into ICC into dm by d. Therefore, the instantaneous torque Ti equal to, what is IP? Root 2 IP into sin omega t. Then what is ICC? Root 2I into sin omega t minus pi into dm by d theta. Then you simplify this one. The instantaneous torque Ti equal to 2 into IP into I into S sin omega t minus pi into dm by d theta. Then the instantaneous torque Ti equal to S IP into I into 2 sin omega t S sin omega t minus pi into sin omega t minus pi into dm by d theta. Then by simplifying this one, the instantaneous torque Ti equal to 2 sin A sin B cos A minus B minus cos A plus B. Then what do you get? IP into I into cos A minus B cos pi minus cos A plus B is cos 2 omega t minus pi into dm by d theta. Okay, this is the expression for instantaneous torque produced in EDM instrument. This is equation 1. This IP Ti equal to IP into I into cos pi minus cos omega t minus pi into dm by d theta. Cos A minus B minus cos A plus B. This much of instantaneous torque is produced. But I want average torque. Then average deflecting torque equal to average deflecting torque equal to, tell me, How to get expression for average deflecting torque? TD equal to 1 by 2 pi s integral 0 to 2 pi Ti d omega t. Okay, but I want not instantaneous torque, we want average deflecting torque. Then it's over, quick, note down. As TD equal to, one more step I am writing here, TD equal to 1 by 2 pi integral 0 to 2 pi, what is Ti? Yes, Ip into I into cos pi minus cos 2 omega t minus pi into dm by d theta into d omega t into d omega t. Okay, now I am calculating average deflecting torque in a wattmeter. Yes, it's over. Now continue this. Then what is the average deflecting torque TD equal to? You write 1 by 2 pi integral 0 to 2 pi cos pi, that is Ip into I into this, you bring that Ip into I into dm by d theta is constant, this integral I am writing 1 by 2 pi integral 0 to 2 pi cos pi d omega t minus 1 by 2 pi integral 0 to 2 pi cos of 2 omega t minus pi d omega t. This over d omega t. Okay, I am writing that expression separately. Then what is the average deflecting torque? TD equal to Ip into I into dm by d theta into this, integrate and substitute the limits, we can get cos pi. This integration of cos in one cycle, integration of cos in one, cos pi is constant. This cos pi is constant. Understood? Cos pi is constant, d omega t limits are d omega, integration of constant is omega t, that is omega t pi to, write one more step I am writing here, 1 by 2 pi, 1 by 2 pi, that cos pi is constant na, 1 minute please, this cos pi is constant na, cos pi is constant, that cos pi by 2 pi, integration of constant is omega t 0 to 2 pi, this minus this integration of cos 2 omega t in one cycle, cos function in one cycle 0. Then what is the deflecting torque? TD equal to Ip into I into cos pi into dm by d theta. Okay, this is the deflecting torque equation of wattmeter. Let this is equation 2. This is deflecting torque equation of wattmeter. Deflecting torque equation of wattmeters. TD equal to Ip into I into cos pi into dm by d theta. Yes. Now tell me. This is the deflecting torque. This much of torque, average deflecting torque is produced in wattmeter. Now I want to prove that this meter measuring the AC power. Now tell me, what type of controlling torque we are using in wattmeter? Spring control. Yes. For spring control. For spring control. Yes. TC equal to K theta. Then at steady state, TC equal to TD. Yes, what is Tc? K theta. What is Td? Ip into I into cos pi into dm by d theta. Then what is theta equal to? Ip into I by k cos pi into dm by d theta. Shall you write like this? Theta equal to, what is Ip? You can write V by Rp. V by Rp. That is Vi cos pi by KRP dm by d theta. Okay, this is the deflection of a pointer with assumption of pressure coil inductance is negligible. If the pressure coil inductance is negligible, then the deflection of a pointer indicating which power? Vi cos pi. Vi cos pi is nothing but a true power, true AC power. That's why this deflection of a pointer gives the true power. This is the expression for true power. Equation 3. When we are getting this true power expression, by assumption of inductance is negligible. By assumption of inductance is negligible means we are assuming that pressure coil is highly resistive. That's why if it is a pressure coil is highly resistive, then you can measure the Vi cos pi. Vi cos pi is a true power. Therefore, theta equal to AC power by KRP into dm by d theta. If dm by d theta equal to constant, the deflection of a pointer indicates tell me, if dm by d theta equal to constant, then theta is proportional to AC power. That is proportional to P. That is theta is proportional to P. Okay, this is the proof. That's why in a wattmeter, the deflection of a pointer directly indicates which power? Active power. That is AC power. That's why hence wattmeter measures the AC power. Clear? The deflection of a pointer is not indicating voltage, not indicating current. The deflection of a pointer indicating the power. That's why it measures the power. Wattmeter measures the power. What is the power? Is input. What is theta? Is output. The input-output relation is linear. Hence, scale is linear. In wattmeter, scale is linear. I told already. If you use electrodynamometer type instrument, scale is non-linear, but the concept is applicable only in voltmeter and ammeter. The same electrodynamometer is used as a wattmeter, the scale becomes linear. With respect to wattmeter, it is a linear scale. With respect to voltmeter and ammeter only, scale is non-linear in the case of electrodynamometer type instrument. But simply remember like this, in wattmeter, scale is linear. Okay. Now, here theta is proportional to P means P is which power here? Active power. P is which power? Active power. That's why wattmeter measuring which power? Active power. Wattmeter measures active power. Measures active. I am talking about single wattmeter, single phase. Active power. That Vi cos pi expression is active power. It's not reactive power. Okay. This about how to measure the power by using the wattmeter. Here I want to give some summary. This you taken as a summary 1. During preparation mainly concentrate on summary 1 and summary 2. If you want concept means whatever the concept I am explaining that you concentrate. To solve any problems mainly concentrate on summary 1 and summary 2. This I am giving summary 1. First one. What is the deflecting torque equation of EDM wattmeter? The deflecting torque TD equal to IP into I into cos pi into dm by d theta. Next, this is a deflecting torque equation. TD equal to IP into I into cos pi into d. Then what is the true power expression? True power equal to Vi cos pi by KRP into dm by d theta. Very important. The expression for true power is Vi cos pi by KRP into dm. That is, if you make dm by d theta and KRP is constant, then true power equal to Vi cos pi, where pi is the power factor angle. Okay, next. Theta is proportional to P. That is, in wattmeter, scale is linear. Scale is linear. Next. Wattmeter measures active power. Wattmeter measures active power. Meter measures active power. Active power. Then fifth statement, very important statement. Then whatever the power measured by wattmeter, we are getting expression for theta equal to Vi cos pi by KRP into dm by d theta. Na. How we are getting this expression? For instantaneous torque, by calculating which value? For instantaneous torque, Ti equal to Ip into, that is Ti equal to Ip into Icc into dm by d theta. Na. For that instantaneous torque, what value you are calculated? Average value or RMS value? Average. That means by calculating the average value only, we are getting the expression for instant. We are getting the expression for true power. That's why it is average power measuring and average power indicating meter. Very important to solve the problems. It is average power measuring and average power indicating meter. Power indicating meter. That means wattmeter measures the average power. But you have the one doubt, sir. In wattmeter measuring Vi cos pi, where V is RMS value, I is RMS value. But you are telling that Vi cos pi is average value. Yes. Even though V is RMS value and I is RMS value, no doubt at all. But Vi cos pi is not RMS power, it is average power. Understood? That's the reason why it is average power measuring and average power indicating meter. To solve the one modular problems based on the wattmeter, this statement is important. Next, last observation. We are getting a Vi cos pi expression with the assumption of pressure coil inductance is negligible. But practically, every coil will offer some inductance. But here I taken the assumption is pressure coil inductance is negligible, then only we are getting the expression for true power. That's why to measure the true power, pressure coil must be highly resistive. To measure the true power, pressure coil must be highly resistive. Then only we can measure the true power. Yes. Td equal to Ip into I into cos pi into dm by d theta. What is the true power expression? Then what is the scale? Wattmeter measures active power. It is average power measuring and average power indicating meter. To measure the true power, pressure coil must be highly resistive. Then only we can measure the true power. Okay. This is case 1. In the case 1, what I given? By assumption of pressure coil inductance, assuming that lagging power factor load, then we proved that wattmeter measuring the active power and it is average power measuring and average power indicating meter. If you want to concept means you concentrate on these steps. But if you mainly concentrate on computative point of means concentrate on summary. Clear? Quick note down. Okay, next we go for case 2. Yes. We'll see the case 2. Here pressure coil inductance is not neglected. Case 2 is pressure coil inductance is not neglected. With this assumption I am explaining. And loads must be, case 2 is also lagging loads. I am explaining lagging power factor loads. For leading loads directly I will give the expressions how to write. Lagging power factor loads only. Okay. Now, if the pressure coil inductance is not neglected means, let the pressure coil impedance is, what is Zp equal to? Rp plus Jxp. That equal to Rp plus J omega Lp. We are not neglecting the pressure coil inductance. Now, if you draw the impedance triangle of pressure coil, this is Rp and this is Xp. This one is Zp. This angle is beta. Now, what is cos beta from this, you tell me? Cos beta equal to Rp by Zp. What is tan beta, you tell me? Xp by Rp. Okay. Now, if you draw the impedance triangle, now if you draw the vector diagram in this case, let the V is the supply voltage. V is the supply voltage. Then we are assuming that lagging loads. Yes. Pressure coil inductance is not neglected. If the pressure coil inductance is not neglected means, now you tell me in this case, what is the pressure coil current? Lags the voltage or leads the voltage or in phase with the voltage? Yes. Pressure coil is inductive nature. We are not neglected. That's why it is a lagging. Then pressure coil current. But we cannot design with high inductance. Pressure coil is designed with very small inductance. What is the reason? Yes. If it is highly resistive, then only we can measure the true power. That's why it must have very small inductance only. That's why it is lagging. Then what about the load current is also? Load current also lags the voltage by angle of pi. Now what is the angle between Ip and I? Pi minus beta. This is small, this is large. As compared to load inductance, the pressure coil inductance is very less. It is a negligible inductance. That's why, but I want to do exact analysis. That's why I am considering this angle also. Ip lags V, I is also lags V. Why? Because of lagging loads. Why Ip lags V? Because we are assuming that pressure coil inductance, having some inductance. Now, the angle between Ip, this is pi, this is beta. Now, this angle is pi minus beta. The angle between Ip and I is pi minus beta. This is the angle. Now, again, no need to derivation. Directly you write the expression for torque equation in this case. Can you write the expression for torque equation? Now, what is the deflecting torque produced? Td equal to Ip into I into, actually in the case 1, what is the expression we are getting? Cos pi. Because where the angle between Ip and I is pi. But now what is the angle between Ip and I? Pi minus beta. Is it to write? Then cos of, yes, pi minus beta into dm by d theta. This is the deflecting torque equation under the practical case. Case 2 is the practical case. Let this is equation, given equation 1 and equation 2. Now, let you take this is equation 3. Instantaneous torque equation I given, then 2, 3, sorry, this is you take the equation 4. In the case 1, I covered 3 equations, this is equation 4. Then Td equal to Ip into I into cos of pi minus beta into dm by d theta. Here I want to write one statement. If pressure coil is designed with high inductance, then what is the beta? Increases. What about pi minus beta? Decreases. Then what about cos of pi minus beta? Increases. beta increases, pi minus beta decreases, cos of pi minus beta increases, cos of low value gives the high value. That's why then TD is increases. Then what is the deflection of pointer is increases. In this case, the deflection of a pointer indicates true power or measured power. Yes, it's a measured power. True power expression you already seen, but here we don't get true power expression because of pressure coil inductance. That's why theta increases means then measured power is also increases. Why we are getting high power? Because of inductance. Therefore, due to pressure coil inductance, what the observation we are getting? Measured power is greater than true power. For which load this one? Lagging loads. Is particularly for lagging loads, not for leading loads. For leading loads, exactly opposite we can get. Therefore, for lagging power factor loads, measured power is greater than true power. Next, at steady state, I want expression for measured power. That's why I am doing analysis like this. At steady state, then TC equal to TD. Then what is TD? TC K theta. What is TD? IP into I into cos of pi minus beta into dm by d theta. Okay. Now, what is theta equal to? IP into I by k cos of pi minus beta into dm by d theta. Okay. Shall we write like this? Theta equal to, how you can write IP? Yes. Now IP is not V by RP. IP is V by ZP because we are considering inductance also. Then VI by K ZP into cos of pi minus beta into dm by d theta. But I want to get one standard expression. That's why I am simplifying like this. Tell me. This ZP I am writing in terms of RP. You write ZP equal to RP by cos beta, na? ZP equal to RP by cos beta. Then what is theta we can get? Theta equal to VI by K RP by cos beta into cos of pi minus beta into dm by d theta. Shall you write like this? Theta equal to VI by KRP cos beta into cos of pi minus beta into dm by d theta. This is the expression for theta. Now, this theta will indicate in case 2, this is a practical case now. This theta indicates, is it a true power or measured power? Yes, it's a measured power expression. It's not a true power. Then this theta will indicate measured power. Then what is measured power? VI by KRP cos beta into cos beta into cos of pi minus beta dm by d theta. Let this equation 5. Now see the difference. This is the case of with the assumption of pressure coil inductance. But you know that. But what is the true power expression? You already derived this one. VI cos pi by KRP into dm by d theta. This is true power expression. This I already explained this one. VI cos pi by KRP into. This is with the assumption of without LP. This is without LP. We are getting this true power expression. This is the assumption of with LP. With LP. But is it measured power equal to true power? No. Measured power is not equal to true power. But measured power is greater than true power. This I already given because of lagging loads. Now, measured power is not equal to true power because of which inductance? Pressure coil inductance. If the measured power is not equal to true power, there is some error in the power measurement. No? That error is due to which inductance? Yes, pressure coil inductance. Now I want to calculate what is the error due to pressure coil inductance. Clear? Understand what I am telling? Case 1, I am assuming that without any pressure coil inductance, then we are getting the true power expression. But practically that is not possible. That is only ideal case. But practically, what is the power measured by wattmeter that I want to calculate? Then this is the power measured by the wattmeter practically. But this power is not equal to true power. Why this power is not equal to true power? Because of this beta. If beta 0, cos 0, 1, cos pi, then we can get again true power expression. That's why this measured power we are getting because of the pressure coil inductance. The measured power is deviated from the true power because of the pressure coil inductance. Whenever measured power is deviated from the true power, there is some error is introduced in the measurement. That error is mainly due to pressure coil inductance. Now I want to calculate what is the error due to pressure coil inductance. Clear? Okay. Now, in the next session, we will continue with what is the error due to pressure coil inductance. Then I will give the summary 2. Mainly during preparation, we concentrate on summary 1 and summary 2. If you want subject, then you concentrate all the points. Okay. In this session, I explained how the wattmeter measuring the power, then what is the true power expression, what is the measured power expression. This is the measured power and this is the true power. These two are not equal. There is some error is introduced in the measurement. What is that error? We want to calculate. Clear? Thank you. In the next session, we will continue with what is the error due to pressure coil inductance.